There is something deeply strange about the moment we find ourselves in. Right now, somewhere in a clean room in California or Texas or Cape Canaveral, engineers are assembling the most powerful rockets humanity has ever built. Satellites the size of school buses are being placed into precise orbits with margins of error measured in meters. Astronomers are parsing light that has traveled billions of light years to reach a mirror the size of a tennis court, extracting from that ancient photon stream the atmospheric composition of worlds orbiting other suns. We have rovers on Mars sending back images in high-definition dust, rocks, the thin pink sky of a world 40 million miles away, rendered in pixels sharp enough to see the individual pebbles. We have a telescope sitting at the second Lagrange point, a gravitational equilibrium 1.5 million kilometers from Earth. So cold, its instruments hover near absolute zero, and so sensitive it can detect galaxies forming in the first few 100 million years after the Big Bang. The software running on your phone has more raw computing power than the machines that guided Apollo astronauts to the moon and back. By almost any measure, we are an extraordinarily capable civilization. We have taken the raw materials of this planet, iron, silicon, carbon, rare earth elements, extracted from seams in the crust, and shaped them into instruments of almost incomprehensible delicacy. And yet there is a question that does not get asked enough, at least not with the seriousness it deserves. Not the breathless question of when we will reach the stars, or which exoplanet might harbor life, or which generation will be the first to walk on Martian soil. A quieter question, one that sits underneath all the optimism like a stone floor, steady and cold and seldom examined. What if we never leave? Not never leave Earth. We have already done that, in limited, fragile, expensive ways. But what if we never truly leave the solar system? What if the gravitational dominion of our sun and all the vast territory it encompasses represents not just a practical challenge, but something closer to a permanent boundary? What if the arc of human progress, so dazzling in so many dimensions, simply does not have the shape required to carry living beings across interstellar space? This is not a pessimistic question, or rather, it does not have to be. It is, instead, an honest one. And honesty about the scale of what lies between us and any other star system might be the most important intellectual exercise we can undertake, not to discourage ambition, but to understand what ambition is actually up against. Because ambition aimed at the impossible is not nobility. It is a kind of grief postponed. So let us start where honesty requires us to start, which is with the trajectory of progress itself, and why, despite its extraordinary shape over the past 2 centuries, it may not be the guide we think it is when it comes to this particular challenge. Consider what has happened in the span of a few human lifetimes. In 1800, the fastest a human being could travel over any significant distance was roughly the speed of a horse, perhaps 50 kilometers per hour on a very good day, on a flat road with a fresh animal. By 1900, trains were routinely exceeding 150 kilometers per hour. By 1960, passenger jets were cruising above 800. By 1969, a rocket had accelerated 3 human beings to the speed required to escape Earth's gravity and reach the moon in 3 days. The acceleration of top speed over those 170 years was astonishing. More than tenfold in a century, more than tenfold again in the next half-century. In computing, the acceleration was even more dramatic. The first electronic computers of the 1940s could perform a few thousand operations per second, occupied entire rooms, and required constant maintenance from teams of engineers. By the time of this narration, a consumer laptop performs trillions of operations per second, fits in a bag, and runs for hours on a battery that weighs less than half a kilogram. The improvement in raw processing capability from the 1940s to now represents something in the range of 10 to the 12th power, a trillion-fold increase in about 80 years. Communication, medicine, materials, science, energy production, similar stories, similar trajectories. And it is not just speed and computing. The materials we build with have transformed in ways that would have seemed like sorcery to previous generations. Carbon fiber composites that are stronger than steel at a fraction of the weight. Superalloys engineered to maintain structural integrity at temperatures hot enough to melt aluminum. Metamaterials that bend light in ways no natural substance permits. We design drugs by modeling molecular interactions on computers and then synthesizing compounds atom by atom. We edit the genomes of living organisms with a precision that was literally undreamed of 3 decades ago. We peer into the interiors of stars using neutrinos particles so weakly interacting they pass through the entire Earth with almost no resistance, detected by devices sunk into deep mines to shield them from background noise. Every one of these capabilities would have seemed miraculous, or insane, or simply incoherent to someone from 1800. And yet here they are, not in science fiction but in operating laboratories and hospitals and factories. The catalog of things humans have accomplished is so extraordinary that optimism about the future of technology is not naive. It is, in many ways, the rational response to the evidence. It is entirely natural, when you look at that history, to assume that the same exponential logic will eventually carry us to the stars. That whatever seems impossible today will, in 100 years, seem merely difficult, and in 500 years will seem entirely routine. That the generation ships and antimatter drives and laser-propelled light sails of science fiction are not fantasies but predictions early, rough predictions, but predictions nonetheless. We have been conditioned by our own history to expect that the next wall will fall the way every previous wall fell, and that beyond each horizon there is simply another horizon, equally crossable. But there is something categorically different about the wall of interstellar travel, something that sets it apart from all previous challenges, not in degree, but in kind. And it is not, at its deepest level, a problem of engineering. It is a problem of physics. Specifically, it is a problem of energy, distance, and the structure of space-time itself. 3 categories that do not respond to innovation the way materials and software and manufacturing processes do. You cannot disrupt physics. You can understand it more deeply. You can find its unexplored corners. But you cannot iterate around the laws of thermodynamics or special relativity the way you iterate around an inefficient supply chain. The speed of light is 299,792 kilometers per second. That number, written plainly, sounds almost manageable. It sounds fast enough to bridge the distances between stars in some tolerable span of time. But the galaxy is not measured in kilometers, and the intuitions we carry from daily life, intuitions built on a planet where a fast car goes 150 kilometers per hour and a fast jet goes 900, break down completely at cosmic scales. They do not just underestimate, they fail so catastrophically that they become actively misleading. There is something additionally clarifying about understanding what special relativity actually says about travel at high speeds. As a spacecraft accelerates toward the speed of light, several things happen that ordinary intuition cannot prepare you for. Mass increases, time dilates, clocks on the spacecraft tick slower than clocks at home, which has the perverse effect of making very long journeys more survivable for the crew while making them even more disconnected from the civilization that launched them. A crew traveling at 99% of the speed of light to Proxima Centauri would age only about 7 months, while about 4.3 years would pass back on Earth. At 99.9% of light speed, the crew ages only about 7 weeks for the same trip. This is genuine physics, not metaphor. It has been verified in particle accelerators thousands of times with unstable particles that live much longer when moving fast. But the energy required to reach 99% of light speed for any significant mass is not 7 times greater than the energy to reach 90% of light speed. It is not 70 times greater. The required energy climbs toward infinity as velocity approaches the speed of light, according to the equations that Einstein derived in 1905, and that every physics experiment since has confirmed. The universe does not offer shortcuts around this. It offers the equations, and the equations do not negotiate. The nearest star system to our own is the triple system of Alpha Centauri, the closest component of which, a dim red dwarf called Proxima Centauri, sits about 4.24 light-years away. That is the distance light moving at 299,792 kilometers per second covers in 4.24 years. More than 4 years, at a speed so extreme that it can circle the entire circumference of the Earth 7.5 times in a single second. That is how long it takes light to make the crossing, not a spaceship. Light itself. Our fastest spacecraft, Voyager 1, launched in 1977 and now more than 160 astronomical units from the Sun, is currently moving at roughly 17 kilometers per second relative to the Sunday. That speed was achieved by a series of gravitational assist slingshots around Jupiter and Saturn that used the planet's own orbital momentum to fling the spacecraft outward. There will not be planets to slingshot off of in interstellar space. But even taking Voyager 1's current speed as a baseline, and it is one of the highest sustained speeds any human-made object has ever achieved, if it were aimed at Proxima Centauri, which it is not, it would take approximately 73,000 years to arrive. Not several generations, not centuries. 73,000 years. That is longer than anatomically modern humans have existed in anything resembling organized societies. It contains the last ice age, the entire Holocene epoch, the invention of agriculture, the rise of every civilization in recorded history, the Industrial Revolution, the Digital Revolution, and everything that comes after, stacked on top of each other, and then stacked again until the pile is 30 or 40 times taller than all of recorded history combined. 73,000 years for the fastest thing we have ever launched into space, to reach the nearest star. To make that crossing in any span of time that could plausibly be called a mission, say, within a human lifetime, or even within several generations, a spacecraft would need to travel at somewhere between 1 and 10% of the speed of light. At 1% of light speed, a voyage to Proxima Centauri takes about 424 years. At 10%, about 42 years. 1% of the speed of light is roughly 3,000 kilometers per second. That is 176 times faster than Voyager 1. And here is where the physics becomes genuinely, implacably difficult. The Tsiolkovsky rocket equation, formulated in 1903 by a Russian schoolteacher working in a small town outside Moscow, describes the relationship between a rocket's exhaust velocity, the ratio of its initial to final mass, and the velocity change it can achieve. It is a simple equation, elegant even, and it is one of the most sobering results in applied mathematics. What it tells you is that the relationship between propellant mass and achievable velocity is exponential, not linear. Every additional increment of speed requires a disproportionate increase in fuel. The fuel itself is mass that must be accelerated, so you need fuel for the fuel, and fuel for the fuel's fuel, and so on, in an unforgiving regression. For chemical rockets, which release energy through rearranging chemical bonds, the same basic process that powers any combustion, only much faster, the exhaust velocity is limited by the energy content of those bonds. The best chemical propellants, burning liquid hydrogen with liquid oxygen, have an exhaust velocity of around 4.5 kilometers per second. With those numbers in the rocket equation, getting a spacecraft to 1% of the speed of light would require a fuel-to-payload ratio so extreme as to be physically nonsensical, not just impractical, but impossible in the sense that you would need more mass of propellant than exists in the observable universe by many orders of magnitude. Nuclear propulsion helps. Fission reactions release vastly more energy per unit mass than chemical reactions, roughly 1,000,000 times more. Fusion releases more still. Project Orion, a serious study from the late 1950s and early 1960s, proposed detonating nuclear bombs behind a spacecraft and riding the pulses of plasma. It was, by the standards of propulsion engineering, not a completely unreasonable idea. The physicist Freeman Dyson, who worked on it, believed it could eventually reach speeds of a few percent of light speed with the right configuration. But the masses and scales required for anything approaching interstellar velocities were staggering, and the project was abandoned for both political and practical reasons. Among them, the Partial Test Ban Treaty, which made nuclear detonations in space illegal, and the sheer engineering difficulty of building a pusher plate that could survive thousands of nuclear detonations in sequence. The most energetically favorable propulsion concept physicists have seriously considered is the matter-antimatter rocket. When matter meets its antimatter counterpart, the result is complete mutual annihilation. 100% of both masses converted into energy. That is the theoretical maximum energy density that physics permits. Nothing releases more energy per unit mass because nothing converts mass more completely. And even with that theoretical perfection, getting a crewed spacecraft of reasonable size to Proxima Centauri within, say, a century would require manufacturing and transporting quantities of antimatter that are currently, and may for a very long time, remain essentially beyond reach. We produce antimatter now in particle accelerators at places like CERN. We can create anti-hydrogen atoms and study their properties. The quantities involved are measurable in nanograms, achieved at costs that work out to tens of billions of dollars per gram, and that figure assumes particle accelerators running at current scales for years to produce that nanogram. The quantities required for an antimatter rocket to reach even a few % of light speed would be measured in tons. The gap between nanograms and tons is not a gap that clever engineering can close in any obvious time frame. Producing antimatter requires vast amounts of energy to begin with. You are not generating fuel in the conventional sense, but converting energy into mass, which is the reverse of what rockets typically do, and the conversion efficiency is poor. The storage problem is equally severe. Antimatter annihilates on contact with any ordinary matter and must therefore be held in electromagnetic traps in perfect vacuum indefinitely, with no failure modes tolerated, for a voyage that might last decades. The storage problem is equally severe. Antimatter annihilates on contact with any ordinary matter and must therefore be held in electromagnetic traps in perfect vacuum indefinitely, with no failure modes tolerated, for a voyage that might last decades. There are other propulsion concepts worth mentioning, not because they are more plausible than antimatter, but because they illustrate the range of ideas serious physicists have considered. Laser sail propulsion, accelerating a thin reflective sail using a powerful laser array, could theoretically push a small probe to a few % of light speed without the probe carrying any fuel at all. The Breakthrough Starshot initiative, announced in 2016, proposed exactly this: a ground-based laser array delivering petawatts of power to a gram-scale sail, pushing it to around 20% of light speed, reaching Alpha Centauri in roughly 20 years. The concept is legitimate physics. The engineering challenges are not trivial: building a laser array of sufficient power, keeping the sail stable and aimed over the required acceleration distance, surviving the interstellar medium at those speeds, and transmitting any data back from 4 light-years away. But the approach at least does not obviously violate any physical law. The problem is scale. A gram-scale probe can carry no meaningful instrumentation, and certainly no human beings. Scaling up from grams to kilograms multiplies energy requirements enormously. Scaling to a crewed spacecraft makes the numbers astronomical in the least comfortable sense of the word. The Alcubierre drive a theoretical space-time metric proposed by physicist Miguel Alcubierre in 1994, which would contract space in front of a spacecraft and expand it behind, moving the vessel faster than light, without the vessel itself exceeding light speed locally, is mathematically consistent with general relativity and has received genuine attention. It is also, on current understanding, entirely beyond physical realization. The exotic matter required to create the warp bubble has negative energy density, a property that may not be achievable for any macroscopic quantity of matter. The energy requirements, if the exotic matter could be obtained, would exceed the mass energy of Jupiter. It remains a beautiful mathematical object with no known path to engineering. This is the physics situation, stripped of comfortable optimism, not absolutely impossible. Perhaps there may be approaches that remain unconceived, corners of physics not yet mapped. But the barriers are not barriers of insufficient cleverness or insufficient funding. They are barriers written into the structure of reality, and facing them honestly is a prerequisite for thinking clearly about what the future of exploration actually looks like. Now step back from the question of interstellar travel and consider something more immediate. The solar system itself, the territory we might plausibly begin to explore seriously within the next few centuries. Because most people carry around a mental image of the solar system that is so profoundly wrong, it makes everything else harder to understand correctly. The image comes from school diagrams: a yellow circle at the center, then a small gray dot close in, which is Mercury, then a white dot, Venus, then a blue dot, Earth with its small companion, then a red dot, Mars, then, after a bigger gap, the ringed majesty of Jupiter and Saturn, the pale blue smears of Uranus and Neptune. Everything depicted within a neat oval on a page or screen, everything scaled to fit, everything appearing to exist within a comprehensible space. The problem with that image is that it is not merely simplified. It is wrong by a factor that exceeds most people's ability to process intuitively. The actual solar system, the territory shaped by the gravitational influence of the Sun, extends to distances that make the 8-planet system look like an error of rounding. Let us work outward carefully and try not to lose our grip on the scales involved. Earth orbits at about 150 million kilometers from the Sun. That is 1 astronomical unit, the baseline distance used in solar system measurement. Mars, our nearest neighbor outward, orbits at about 1.5 astronomical units. Jupiter, the largest planet, at about 5.2, Saturn at 9.5. Neptune, the outermost major planet, at roughly 30 astronomical units from the Sun, that is 4.5 billion kilometers, 30 times the distance from Earth to the Sun. The number is almost too large to mean anything. Light takes 8 minutes to reach Earth from the Sun, and more than 4 hours to reach Neptune. Beyond Neptune lies the Kuiper Belt, a vast disk of icy bodies extending from roughly 30 to about 50 astronomical units. This is the home of Pluto, Eris, Makemake, Haumea, and hundreds of thousands of smaller objects catalogued and uncatalogued. The Kuiper Belt is not a thin ring of scattered debris. It is a complex, dynamically active region of primordial material left over from the solar system's formation, containing more mass than many realize and presenting genuine challenges for any spacecraft trying to navigate through it at high speed. The outer edge of the Kuiper Belt sits at roughly 50 astronomical units. That is 7.5 billion kilometers from the Sunday Voyager 1, moving at 17 kilometers per second, and now more than 160 astronomical units out, passed through the Kuiper Belt decades ago. The spacecraft is now in what astronomers call the region beyond the heliopause, the boundary where the solar wind, that constant outflow of charged particles from the Sun, has been halted by the pressure of the interstellar medium pushing back against it. This boundary sits at roughly 120 astronomical units. Voyager 1 crossed it in 2012, becoming the first human-made object to enter interstellar space in this specific and limited sense. But the heliopause is not the edge of the solar system, not even close. Beyond it, stretching outward in a roughly spherical shell around the entire solar system, lies the Oort Cloud. And this is where scales become genuinely difficult to convey without losing something essential in the telling. The Oort Cloud is thought to extend from somewhere around 2,000 astronomical units to somewhere between 50,000 and 200,000 astronomical units from the Sun, the inner boundary populated by scattered disk objects, and the outer boundary defined by the limits of the Sun's gravitational grip against the competing gravity of nearby stars and the galaxy's own tidal forces. 200,000 astronomical units is 30 trillion kilometers. At that distance, the Sun's gravity is so weak that the objects in the outer Oort Cloud orbit, with periods measured not in years, but in millions of years. A single trip around the Sun for an object at the outer boundary takes longer than the Earth has existed. These objects, billions of them, perhaps trillions, icy bodies ranging from pebbles to small worlds, have been drifting in that vast cold darkness since before the solar system reached its current configuration. They have never been visited, never been directly imaged, barely been detected at all except through the long elliptical paths of long-period comets that fall sunward from that distant reservoir when gravitational perturbations from passing stars, from the tidal forces of the galaxy itself, nudge them out of their stable orbits and send them plummeting inward. Think about that for a moment. Objects that have been orbiting in silence for 4.5 billion years occasionally fall inward and light up our sky as comets. Halley's Comet, visible from Earth with the naked eye every 76 years, is a fragment of material that formed when the solar system formed, spending most of its existence in the cold outer regions before its current orbit was established. It carries within its ice and rock a chemical record of the early solar system amino acids, complex organic molecules, the precursor chemistry of life, frozen and preserved for billions of years in temperatures near absolute zero, and we have barely begun to read that record. The outer Oort cloud sits at roughly 1.6 light-years from the Sunday, that is almost exactly halfway to Proxima Centauri. The solar system, in its full extent, reaches to the halfway point between us and the nearest star. Its gravitational dominion extends further than most people imagine when they think about leaving the solar system. Voyager 1, which has been traveling for nearly 50 years, has not yet begun to enter the Oort cloud's inner edge. By even optimistic estimates, it will not reach the inner Oort cloud for several hundred years. It will not exit the outer Oort cloud for perhaps 30,000 years. These are the distances we are talking about. This is the solar system, not the tidy diagram from the textbook, but the real thing, a structure so vast that our most distant spacecraft is still, in a meaningful sense, a stone's throw from home. To mount any serious program of interstellar exploration, even granting some extraordinary breakthrough in propulsion, would require energy on a scale that deserves its own careful attention, because the energy requirement, more than any other single factor, is what makes the challenge feel not merely difficult, but qualitatively different from every other challenge human civilization has attempted. In 1964, Soviet astronomer Nikolai Kardashev proposed classifying civilizations by their energy usage. A Type 1 civilization fully harnesses all the energy available on its home planet, every joule of sunlight, geothermal energy, wind, and tidal force. A Type 2 civilization harnesses the complete energy output of its star. A Type 3 civilization controls energy at the scale of an entire galaxy. These are rough categories, but they are useful for orienting oneself within the scope of what cosmic expansion actually requires. Humanity sits right now at roughly 0.73 on this scale, substantially below Type 1, meaning we use a significant fraction of Earth's available energy, but have not yet approached anything like full utilization. Our total global energy consumption is approximately 2 times 10 to the 13 watts. The Sun radiates 3.8 times 10 to the 26 watts in all directions. Earth intercepts roughly 1/2 billionth of that, about 1.7 times 10 to the 17 watts, and we use a tiny fraction even of that. A Type 2 civilization would harness the full output of the Sun, which represents roughly 10 trillion times our current energy usage. To accelerate a crewed spacecraft of any realistic size to even 1% of the speed of light using any currently understood propulsion method would require an energy expenditure approaching our entire global energy output for a single launch. A sustained program of interstellar missions would require energy production at scales that constitute a fundamentally different kind of civilization, not a richer version of what we are now. Something qualitatively transformed, organized around energy production and management at scales we cannot currently inhabit, even in imagination, in any operational sense. And ascending the Kardashev scale is not simply a matter of building more solar panels and wind turbines and nuclear plants. Those technologies scale linearly. The distances between Kardashev levels are logarithmic. Getting from 0.73 to 1 requires not a modest improvement, but an improvement by a factor of roughly 10,000. Getting from 1 to 2 requires an improvement by a factor of another 10 billion or so. The engineering vision associated with a Type 2 civilization, Freeman Dyson's concept of a sphere or swarm of collectors completely surrounding the Sun and capturing its entire output, implies an industrial capacity and a coordination mechanism that has no analog in anything humans have built or are seriously planning to build on any near-term timeline. It implies having already solved, in practice, almost every major challenge currently facing our species. We have not done any of that. We are not close to doing any of that. Some of it we may be able to do within centuries. Other parts may prove impossible even given centuries. For reasons that have nothing to do with intelligence or effort, and everything to do with the physical and social constraints on what any civilization can realistically achieve. But even if we imagine generously that all of this is eventually solved, the energy, the propulsion, the shielding there remains a set of problems that are not about machines or power plants at all. They are about the creatures inside the spacecraft. The human body evolved on a planet with a specific gravitational field, 9.8 meters per second squared, without exceptions over 1 billion years of evolutionary history. Every system in the human organism, bone density maintenance, cardiovascular function, fluid distribution, vestibular processing, immune regulation, circadian rhythms is calibrated to operate in that gravitational environment, under that atmospheric pressure, within that narrow band of radiation exposure. We are not generalist organisms capable of thriving across variable conditions. We are extraordinarily specialized creatures, shaped to within a narrow band of conditions by a selection process that had no reason to build in any flexibility toward the vacuum. In microgravity, the body begins to change immediately. Within days, fluid shifts toward the head, elevating intracranial pressure in ways that can push against the optic nerves and cause permanent damage to vision, a phenomenon that affects a significant fraction of astronauts who spend extended time on the International Space Station. bone mineral density decreases at roughly 1 to 2% per month, an accelerated version of the osteoporosis that affects elderly people, but happening in fit, young, otherwise healthy individuals who are exercising for hours every day specifically to prevent it. The heart, no longer pumping against gravity, shrinks and weakens. Muscles atrophy at rates that can be partially managed but not fully reversed. Even the gut microbiome, that community of hundreds of species of bacteria that plays roles in digestion, immunity, and even mood, shifts in ways that are only beginning to be understood. These are not problems that engineering can simply engineer around. Building a centrifuge into a spacecraft to simulate gravity is possible in principle and helps with some issues while potentially creating others. The physics of rotating habitats involve complex interactions between gravity, gradients, Coriolis effects, and human vestibular systems that are not fully worked through. Shielding against radiation is partially possible, but not fully. The galactic cosmic rays that fill interstellar space high-energy particles accelerated to near light speed by distant supernova shockwaves penetrate even substantial lead shielding. Over a decade-long voyage, the accumulated dose would elevate cancer risk to levels that are not acceptable by any current standard and might produce neurological damage that compromises cognitive function before arrival. There is also the psychological dimension, which gets less attention than the physiological, but may be equally constraining. Human beings are social animals in a very deep sense, not just culturally, but neurologically. We evolved in groups of somewhere between 50 and 150 individuals in environments where we could go outside, where the sky changed, where seasons turned, where there was genuine novelty in the physical world. Our brains developed their architecture in that context, and there is growing evidence that the absence of those conditions, real horizon, genuine outdoor space, contact with natural environments, the ability to be truly alone when desired and truly together when desired, has measurable effects on mental health that do not fully respond to substitutes. The Concordia Research Station in Antarctica has been used as a proxy for long-duration space missions. The extreme isolation, the 6 months of polar darkness, the small crew in a confined space it produces, documented psychological effects including depression, cognitive slowdown, interpersonal conflict that is disproportionate to its triggers, and a condition researchers call winter over syndrome, a kind of emotional flattening combined with heightened irritability. And Concordia is on Earth. It can be evacuated in an emergency. Its inhabitants know that the outside world continues just beyond reach. A crew on a 50-year voyage to another star has none of those psychological anchors. These are not problems that can be solved by selecting the right crew. Human psychology does not vary that widely. We are all running similar software on similar hardware, and that hardware was not designed for the environment of a multi-generational metal cylinder hurtling through interstellar space. Solutions exist in the theoretical space. Suspended animation, which would reduce metabolic activity and therefore radiation sensitivity. Genetic modification, which might alter cells to be more radiation resistant. Uploaded consciousness, which would sidestep biology entirely. Each of these belongs to a different degree of speculation. Suspended animation for humans runs into fundamental problems with the complexity of the neural architecture that supports consciousness and memory. The brain is not a tissue that freezes and thaws cleanly. Wood frogs can survive being frozen because their brain architecture is incomparably simpler. Tardigrades survive cryptobiosis because their cellular systems are organized around stress tolerance in ways mammalian cells are not. Whether any form of long-duration human suspension is achievable without catastrophic neurological consequence is not known. We have no experimental data, no animal models that translate clearly to human neurology, no theoretical framework that confidently predicts the outcome. And the generation ship scenario, sending a self-sustaining community of hundreds of people on a multi-century voyage with the expectation that their descendants will complete the journey, introduces problems that are biological and social and ethical in equal measure. The genetic diversity required to sustain a healthy population across many generations without bottleneck effects imposes minimum population sizes that scale the spacecraft enormously. The social dynamics of a community permanently isolated, with no possibility of meaningful external contact, no ability to leave, no ability to renegotiate the terms of the mission, are simply unknown. We have run experiments on isolation, Antarctic overwinter stations, submarine deployments, long-duration space station stays. None of them approximate the absolute irreversibility of a multi-generational interstellar voyage. And none of them address the deepest ethical issue: the people born in transit, the generations who live their entire lives between stars, never chose the mission. They are conscripted by the choices of ancestors they never knew, bound to a destination they did not select, with no option to reconsider. These problems do not have obvious solutions. They are not the kind of problems that get solved by better materials or more clever software. They are problems that run into the deep grain of what human beings are and what kinds of conditions human psychology can sustain over meaningful timescales. There is one more dimension to consider, and it is the strangest and perhaps the most disquieting. It is not about physics or biology or energy. It is about motivation and what we can infer about the long-term shape of civilizational desire. The Fermi paradox has been a puzzle in the philosophy of science since physicist Enrico Fermi first posed it informally in the early 1950s, reportedly over lunch with colleagues, with the simple and devastating question: where is everybody? The observable universe is approximately 13.8 billion years old. Stars capable of supporting life similar to ours have existed for perhaps 10 billion years. The Milky Way alone contains somewhere between 200 and 400 billion stars, and a significant fraction of them host planets in what astronomers call the habitable zone, the range of orbital distances where liquid water could exist on a rocky surface. By conservative estimates, there are tens of billions of potentially habitable planets in our galaxy alone. Given the number of candidates and the length of time available, simple probabilistic arguments suggest that technologically advanced civilizations should be common, and that at least some of them should have had more than enough time to spread across significant portions of the galaxy, even at speeds far below the speed of light. But we detect no signals. We see no megastructures. We encounter no evidence, despite increasingly sensitive searches across multiple wavelengths and methods, that any intelligence beyond our own has made its presence felt anywhere in the cosmos we can observe. Many explanations have been proposed. Perhaps life is genuinely rare. The emergence of cells, of eukaryotic complexity, of multicellular animals, of nervous systems and intelligence, may each represent such improbable leaps that very few lineages have made all of them in the sequence required. Perhaps civilizations regularly destroy themselves through nuclear war, through engineered pandemics, through ecological collapse before reaching the technological threshold required for interstellar travel. Perhaps they retreat inward, into virtual realities or inner space, and simply lose interest in the physical cosmos. Perhaps they exist but communicate in ways we have not yet learned to detect or have consciously chosen silence. But there is a possibility that sits quietly among all these others and deserves more attention than it typically receives. It is the possibility that interstellar expansion, even for civilizations that could physically accomplish it, is simply not something that advanced intelligence chooses to do. Not because they are incapable, but because the cost-benefit calculus, if such a thing applies to entities far beyond our current form, does not support it. Consider the problem from first principles. The motivation to expand geographically in human history has always been driven by some form of scarcity. Not enough arable land, not enough resources, not enough safety from competing groups, not enough opportunity within the existing social structure. Expansion was the answer to insufficiency. But a civilization that has achieved the energy abundance required to mount interstellar missions has, almost by definition, solved scarcity in some fundamental sense. It has solved it so completely that the stars do not hold anything it cannot more easily obtain closer to home. Resources? Asteroids and the outer planets contain more of every useful element than any interstellar mission could bring back. Safety? A civilization capable of interstellar travel is presumably capable of surviving asteroid impacts, climate shifts, and most other natural catastrophes without needing backup colonies in other star systems. Adventure? Curiosity? These are real and powerful motivations, but they are also motivations that can be partially satisfied by other means, by probes and telescopes, by the intellectual work of understanding the cosmos from a distance, by forms of experience and discovery that do not require physical presence at 4.24 light-years remove. A civilization centuries or millennia beyond our current form, with cognitive and experiential capabilities we can barely begin to imagine, may have ways of satisfying those drives that make the physical crossing of interstellar space seem like walking to the next town when you can already be there in some richer sense. The assumption that intelligence naturally spreads outward, colonizing every available niche in the galaxy the way life has colonized every niche on Earth, may be wrong in the same way that many confident predictions about the future have been wrong, because it extrapolates forward from a specific phase of development and assumes that phase continues indefinitely. Life on Earth spread because it had to, because the alternative was extinction, because resources were finite and competition relentless. Intelligence is different. Intelligence can choose. And in choosing, it might select something other than the maximum possible physical expansion. None of this is settled. The future is genuinely open in ways that resist confident prediction. There may be aspects of physics we have not yet discovered. There may be propulsion principles that operate outside the constraints of the rocket equation, using properties of space-time that remain as unknown to us now as quantum mechanics was to Maxwell's contemporaries. History is full of revolutions in understanding that rewrote what was considered possible, and genuine humility requires acknowledging that the history of physics may not be finished. But humility also requires sitting with the numbers as they are. Proxima Centauri, 4.24 light-years. Voyager 1's travel time at current speed, 73,000 years. Energy required for relativistic acceleration exceeds total current human energy output for a single mission. Oort Cloud outer boundary, halfway to the nearest star, unreachable by any current spacecraft within a human lifetime or many lifetimes. Radiation dose on a decade-long interstellar voyage, potentially fatal without shielding, we cannot yet build. Human bone density in microgravity, losing 1 to 2% per month. Antimatter production rate, nanograms per year, at tens of billions of dollars per gram. These numbers are not estimates from pessimists. They are measurements. They do not change depending on how ambitious you are feeling. And the solar system, this vast, incompletely charted territory of 8 planets, hundreds of moons, millions of asteroids, billions of Kuiper Belt objects, and perhaps trillions of Oort Cloud bodies remains, for all its scale, a tiny bubble within a galaxy of 200 billion stars, itself one of hundreds of billions of galaxies in the observable universe. We have sent 5 spacecraft toward interstellar space. We have landed on fewer than a dozen bodies in our own solar system. The nearest star remains, in any practical sense, so remote that calling it inaccessible is not pessimism but precision. And the solar system, this vast, incompletely charted territory of 8 planets, hundreds of moons, millions of asteroids, billions of Kuiper Belt objects, and perhaps trillions of Oort Cloud bodies remains, for all its scale, a tiny bubble within a galaxy of 200 billion stars, itself one of hundreds of billions of galaxies in the observable universe. We have sent 5 spacecraft toward interstellar space. We have landed on fewer than a dozen bodies in our own solar system. We have not visited the Kuiper Belt up close. We have never directly imaged an Oort Cloud object. We have not been back to the moon since 1972. The nearest star remains, in any practical sense, so remote that calling it inaccessible is not pessimism, but precision. The gap between where we are and where interstellar travel would require us to be is not a gap that a few decades of ambitious engineering will close. It is a gap measured in civilizational epochs, if it closes at all. And there is something clarifying, not despairing, in acknowledging that. Knowing accurately where you are is the prerequisite for going anywhere. If the boundary of the achievable lies somewhere between the edge of the solar system and the nearest star, then the solar system itself becomes more than a waypoint. It becomes a world, a territory of almost incomprehensible richness and scale that no human civilization has yet approached, understanding, or utilizing. The asteroid belt alone contains more mineral wealth than humanity could process in millions of years at current rates. The moons of Jupiter and Saturn host oceans, atmospheres, geological activity. Titan has rivers of liquid methane-cutting canyons through plains of frozen nitrogen. Europa almost certainly has a liquid water ocean beneath its ice shell, kept liquid by the tidal flexing of Jupiter's gravity. And that ocean has been in contact with a rocky seafloor for perhaps 4 billion years. These places are not consolation prizes for failing to reach the stars. They are vast, complex, strange, beautiful, and profoundly worth knowing. A civilization that spent 10,000 years genuinely understanding the solar system, not visiting it briefly with robots, but inhabiting it, mapping it, living in it, would be a civilization that had done something remarkable and real. There is a particular kind of vertigo that comes from thinking about all of this seriously. Not the exhilarating vertigo of looking up at the Milky Way and feeling small in the best, most enlivening way. The feeling that there is so much out there, so much to discover, so much waiting. Something quieter and less comfortable. The vertigo of beginning to suspect that the universe was not organized around the convenience of the creatures within it. That the stars are not destinations waiting patiently for us, placed at convenient intervals like cities along a highway, but simply other places, other fires, burning at distances that physics keeps sealed behind barriers that may or may not ever yield to any force we can bring to bear. The universe is under no obligation to be accessible. It is simply what it is. Vast, old, indifferent to our schedules, operating on timescales that make the entire history of human civilization look like a single afternoon. In 1977, the same year, both Voyager probes were launched. A team of scientists assembled 2 golden records and attached them to the outsides of those spacecraft. The records carry sounds and images meant to represent humanity to any intelligence that might find them, greetings in 55 languages, music from dozens of cultures including Bach and Chuck Berry, and a Navajo night chant, the sound of surf and rain and wind and a human heartbeat, the image of a human hand raised in greeting, the coordinates of Earth relative to 14 pulsars, so that any intelligence with astronomical knowledge could locate our home. Carl Sagan, who oversaw the project, called it a message in a bottle thrown into the cosmic ocean. He knew the odds. He sent it anyway. Those records are now in interstellar space. They are the furthest traveled objects humans have ever made. Voyager 1's golden record is currently passing through a region of space that no instrument has ever before explored, moving through the thin medium of hydrogen and helium that fills the space between stars, carrying its music and its greetings outward at roughly 17 kilometers per second into a darkness that will, in all probability, never encounter another mind. In 40,000 years, it will pass within about 1.6 light-years of a dim red star called Gliese 445. Not close enough to enter that system. Just close enough to be a neighbor, briefly, in galactic terms, before continuing outward for billions of years more. The records will drift for billions of years, almost certainly undiscovered. The probability of any intelligence ever finding them, given the emptiness of interstellar space, the distances involved, and the rarity of anything at all, is negligible to the point of irrelevance. They are, in the most literal possible sense, a gesture toward the unreachable, and yet the gesture was made. The record was pressed. The music was chosen. The spacecraft was aimed at the dark. It was a statement about what kind of creature we are, one that knows the message will almost certainly never arrive and sends it anyway, because the sending is what we have, because reaching is what we are. Even when what we reach toward is unreachable by any means we currently possess or may ever possess. The Oort Cloud waits, indifferent and ancient. The heliosphere boundary, where Voyager 1 now drifts through a thickening medium of interstellar hydrogen, is just the beginning of a crossing that will take the probe longer to complete than modern humans have existed. Proxima Centauri burns its slow red fire 4 light-years away, orbiting with its small rocky companion, a world that might have liquid water on its surface, that might have been producing chemistry for longer than Earth has existed, and we cannot reach it, not now. Not in any generation anyone alive today will ever know. The number of generations required, at current speeds, beggars any attempt at empathy with those hypothetical distant descendants who might complete the crossing. Maybe the answer to the great quiet question whether we are alone, whether intelligence is rare or common, whether the galaxy is full of minds that simply cannot reach each other, involves 2 truths that are hard to hold simultaneously: that the universe is vast and old enough to contain many forms of life, and that those forms of life are each confined by the same laws of physics that govern us all equally to their own small neighborhoods. Stars separated by distances that no chemistry and no engineering, however brilliant, can make meaningful on the timescales of a biological life. Each flame of mind, burning in its own corner of the dark, unable to light other flames, by existing able to light them only by touching, and touching being precisely what the structure of the universe makes impossibly hard. Somewhere in the outer Oort Cloud right now, a chunk of ice and silicate that formed in the early solar system before the Earth existed continues its long elliptical orbit in absolute silence. It has orbited the Sun perhaps once in the past billion years, moving so slowly through that remote darkness that calling it motion almost seems too energetic a word. The Sun, from where it drifts, is just another point of light brighter than the others, but not dramatically so. It does not know it is part of our solar system. It does not know anything. It will continue that slow arc long after everything we have ever built has been erased, long after the last city and the last machine and the last record and the last memory of us has dissolved back into elements too scattered to be gathered again. The Sun will still burn then, for another several billion years. The ice will still orbit. The space between stars will remain what it has always been. The question of whether we will ever truly leave, whether any version of what we are, however changed and distant from what we currently recognize as human, however transformed by time and technology and pressures we cannot predict, will one day decelerate into the gravity of another star and look back at a yellow point of light and call it something like home, remains open. Genuinely, irreducibly open. We are a young species, and the universe is very old, and neither of those facts is comfortable to sit with for long. What is not open is the scale of what stands between here and there. What is not open is the indifference of the physics involved. What is not open is the strange and perhaps unrepeatable fact that we are, as far as we can tell, the only things in this part of the universe that know any of this, that have measured the distances and worked out the equations and felt the weight of the answer and sent a golden record into the dark anyway, not because it would work, but because it was the truest thing we knew how to do. The nearest star is 4.24 light-years away. The solar system extends, in its full complexity, nearly halfway to that boundary. Beyond the boundary, in every direction, the stars continue ancient and burning and indifferent, lighting nothing but themselves, waiting for no one.